What all do we have here? This is a 100 volt, 2.9 horsepower DC motor. Any of you that's seen my videos or built my constant current sources, this is one of them. But it's been modified in such a way, with these two connections going back to this optocoupler, that I can use pulse width modulation to control the current through the constant current source. Here is my H-bridge. Here is one of my H-bridge circuits. I presented it earlier. N channel, N channel, P channel, P channel. Those two are controlled through optocouplers from this board here. This is a breakout board that I built for an Arduino Nano. Here are my two direction switches. You have 3 LEDs and 3 optocouplers. The Arduino circuit, which is on its own separate 5-volt supply, is completely electrically isolated from the H-bridge, the current source, and the motor. Pulse width modulation is controlled through this 10K pot here. So if we press a switch, and you watch the motor, and you could probably see the current that it drew. Let's do it again. Let's run it all the way up. You notice it draws quite a lot of current when it first starts because it has to move that heavy steel flywheel. This motor came out of a treadmill, by the way. When it's finally fully spinning, it draws a 0.58 amps. Let's reverse it. Let it slow down and stop. Let's hit the other switch. Notice something with the switch. When I press the switch, there's a delay before the direction. These two LEDs are controlling the direction through the H-bridge. Now watch where the motor is barely moving. Let's switch polarity. You notice that when at this speed in particular, you notice that the minute that both LEDs will go off. When that happens, the H-bridge is placed into the brake position. It'll stop the motor from spinning. If I press both switches, by the way, I turn the system off. Let's run this up. Now let's turn this off when it goes into the braking position, like so. It nearly jerked the motor out of my hands. Let's do that again. It still jerked it out of my hands because that's part of the braking function. The two N-channel MOSFETs in the H-bridge, when this is switched off, they are switched on. And what this does is literally shorts the motor windings together. It shunts both motor windings to ground. And you saw the result of the braking action. And it jerked again when I turned it off. Okay, first let's take a look at our Arduino control board. Here is the actual wiring to it. I made up this symbol in my software. Here are my two switches, switch 1 and 2. And I'm using 3 of the outputs. Digital pin 9 is a pulse width modulation out. It controls the constant current source that controls both the motor speed and can be switched on and off to stop the motor. Digital pins 10 and 11 control motor direction. All right, here's the constant current source that I use for this particular demo. We've seen this before, so I'm not going deeply into it. The current through the LM317 is set by this potentiometer, which is the emitter base current of this large PNP transistor, and its collector current is based on IB times HFE. In this way, I can control the motor speed, but I can also cut the power on and off. The constant current source controls both motor speed and power. The max current control is you turn the optocoupler down here on 100% pulse width modulation, and you set this for the maximum current out. I usually use an auto headlight or something that's non-inductive, and I adjust for my maximum current. And so what you're going to do, you're going to go from 0% modulation, which is no output, to 100% pulse width modulation, which is, if I set it for 2 amps, then it's 2 amps at 100% pulse width modulation. All right, pictured here is one of the many H-bridge configurations that I've presented on my website and various videos. I won't go over the complete operation of that again, but you notice again I have 2 input optocouplers, digital in 1 and digital in 2. Again, note that the digital grounds are separated from the big motor power supply grounds. Of course, if I turn on either leave one optocoupler on and one off, I'm going to be turning it, it'll turn on Q3 and Q2, or Q1 and Q4. If I turn them both on, both of these are turned on and do nothing. What gives you the braking action is as follows. When I turn off both optocouplers, both of these output transistors will switch off. Through these 10K resistors, the gates on Q3 and Q4 will both be turned on. This essentially shunts both sides of the motor to ground. And due to inductive reactance and resistance in the motor windings, that's what stops your motor. All right, I'm going to add this additional circuit to this video, even though it was not used in the video you saw earlier. If you look here, here's my constant current source. In this schematic, I used an NPN transistor instead of an optocoupler. What that does is tie the Arduino ground together with the motor power supply ground, but the rest of it works the same. What you see here is with the motor connected back to the constant current source is collectively this, with the 0.25 ohm resistor between the common down here where the transistors connect and ground. This is an LM358 op-amp. This will allow me to read with the Arduino through an analog to digital port the actual current through the motor H-bridge combination. The gain is set by this 100K resistor and that 10K resistor, while this 4.7K and 10 microfarad capacitor form a filter. Let us argue, for instance, that at 2 amps times 0.25 ohms is going to give me a half a volt at 2 amps. For example, as you saw in the video, when the motor first starts and it's having to suck up a lot of energy to get that heavy flywheel moving, you can monitor that kick up in current, and you can time it in such a way that if you know where your run current is, which dropped to, 0.6 amps, if you had this, you could You can set your voltage to wherever you want it on the output. The Arduino can read the output, and that tells it automatically that okay, I'm running at the right current. That doesn't count that you could put a Hall sensor or something on the flywheel to tell the exact motor speed, but in this way you can monitor motor current. What if, for instance, you have some drift in your PNP transistor, and we know this happens at certain currents, and this is monitoring the motor current? The motor's going to start speeding up on you. But Arduino or whatever microcontroller can detect this. If the motor speeds up more than it seems like it should, which means more current, then you just simply program it to cut back the pulse width modulation a little bit to get it back in line. This is your feedback. You know how much current your motor's drawing. You can monitor it. In particular, what if the motor stalls or is in such a heavy load it can barely move? Okay, you're going to be able to, Arduino will know that and immediately think, okay, something is wrong, shut down the power. So it turns off DN in this case to the H bridge. Let's see, what else do we need to do here? As an alternate also, since you already have an Arduino and have lots of pins, why not attach a temperature sensor to your big heat sink out here? And if you find out that the heat sink is really running hot, you can have the Arduino cut on a small cooling fan. Depends on your heat sink configuration. Or you can reduce the duty cycle to get the temperature more controlled. So you can monitor the temperature of the heat sink. That should tell you if something's working right or not. You can monitor the motor voltage current directly, and then you can make the appropriate pulse width modulation adjustments for the circuit. That's all I have for this. Your link is down here. This has the schematics, a written explanation, and additional information. Appreciate you listening to this video, and catch you later.